Okay, so in the second rotational kinematics review question, we have a rotating theme park ride that has initial angular velocity of negative 290 RPMs. Moves with an angular acceleration as shown in the graph below, essentially. Alright. As the magnitude of the angular velocity t equals 7, so we're this is going to be 7 here. Greater than less or equal to the magnitude of the angular velocity at t equals 10 seconds here. So this is an angular acceleration graph, and the area under that curve will give us delta omega. So we have to figure out, use the graph, or use constant angular acceleration kinematics. That's technically what we're using to figure out what are the angular speeds at t equals to 7 and t equals to 10. So since the angular acceleration is in rads per second squared, and the initial angular speeds in RPMs, I'm going to first start with converting that initial angular speed to correct SI units of radians per second. So omega I is negative 290 RPM, which is negative 290. Every revolution has 2 pi radians, and every minute has 60 seconds. So this works out to be negative 30.4 radians per second. Now the angular acceleration is constant for both situations, for the first 7 and from 7 to 10, but they're different values, but they are constant. So to figure out the angular speed at any given time, I can consider knowing that omega f is omega I plus alpha delta t. So in this example, omega at t equals to 7 will be omega I, so at t equals to 0, which is negative 30.4 radians per second, plus alpha for the first one, for the first 7 seconds is 4 radians per second, and the time interval is 7 seconds. So this change here, 4 times 7, is the area underneath this curve, which gives us the alpha delta t is delta omega. So this delta omega is 28 radians per second. So this value works out to be, and your calculations correctly, negative 2.4 radians per second. And then we can do a similar calculation for this angular speed at 10 seconds, but now we have a different initial angular speed. So this will be the beginning angular speed at t equals to 7. So omega at 10 will be equal to that initial speed of negative 2.4 radians per second, plus this alpha now though is negative, so we have a negative 2 radians per second squared, and just notice I missed my square up here in the 4, times a time interval of 3 seconds, and this works out to be, so this will be a negative times another negative quantity, so this ends up at negative 8.4 radians per second. So again, this will change of 6. So that's the area underneath here. The delta omega here is going to be negative 6 radians per second. So overall there's a change of negative 34. A change of 24 radians per second. If I looked at that correctly, no, 22, and that will give you this consistent final speed of negative 8.4 radians per second. But we're trying to compare here the magnitude of the angular velocity at t equals to 7 to that of at t equals to 10. So we can see that the angular velocity at 10, the magnitude of this is 8.4, is larger than that at t equals to 7, which was only 2.4.